Oof. Hey, Justin. Hi, Sarah. APs are almost over. Yay. Hooray. Let's start at 10:05. I mean, not 10:05. Let's start at 10:25 to give everyone a chance to, get their butts over here. Hey, Sylvie. Good morning. Hello, Itamar. Hey, Becky. Hey, Ethan. Good morning. Sorry for the delay. I'm just preparing some tea. I'm deciding on what to drink. I think I will drink Fujimidori. Yes. Sweet. Yum. Grandmaster Chris. Good morning, Yona. So good to see all of you. So hopefully we found that wave generator simulator a little exciting, right? It's like a mini lab where you just kind of get to toy around with stuff, and that's one of the few things it's one of the few topics that we're covering today, or like in the whole year, where the simulation's probably better than the real thing, because it's really hard to get a rope to behave in the ideal way. So first of all, like, why is that? Like, you need it to be really straight. And for most ropes with any sort of non-negligible mass, they're going to dip in the middle. So without like an extremely high tension, right, that you see in like a guitar string or whatever. And the problem is and what you'll see is, well, who can tell me why that's a problem, right? If the only way we get a string to be like really straight is with high tension, why don't we want high tension when we make that kind of demonstration in real life? Answer that in the chat. Why is that a problem? Like, well, why is high tension? So let's say here's the situation, right? I want to recreate the simulation that we did together, not together, but independently yesterday. That was due this morning, and I want to have a straight line, and I want to send a wave through. But the only way to get it like really straight and to get it to behave the way it does in simulation is to have really high tension. So why would it be bad to have that kind of high tension? Good morning, Etienne. Please answer that in the chat while I'm just brewing some tea. No big deal. Hello. So Itamar answered, I'm looking for more answers. He says it would have a high frequency and low amplitude. Remember, the amplitude only depends on what I do. It doesn't depend on anything about the medium, right? So if I increase the tension, it won't change the amplitude at all. I hope that's what you saw yesterday. It would have a high frequency. Again, the only thing that changes the frequency, like how many pulses per second are generated or how many pulses per second I generate on my end of the string. The rope could break. That's not the big problem, right? So let me answer this with you, right? So that's our basic do now for the day. And let's see, classwork PDF. Okay, so I want you to keep that in mind, okay? So that's like our guiding question for the day, all right? So like our do now plus like essential question like why is the simulation better, right? So this is a whole URL versus IRL debate, and this is one of the few things that's better URL, right? Okay, so let's get into it. I want you to have those worksheets ready. I want you to have them out, okay? And let's answer the very first question, okay? And that question is, what is one thing that always remains consistent about the waves that you send from the left side of the string? This is when there's an open end at the right end, right? So then the answer should have been the wave speed, right? No matter, like if you send two pulses, one pulse, a big pulse, a small pulse, or two pulses close together, two pulses far apart, upward pulse or a downward pulse, no matter what you did, the speed of the waves should have remained consistent, right? There's nothing I can do to change my speed because one of the big talking points that I want you to walk away with from this unit, right, is that speed only depends on what, everyone? What does the speed depend on, right? I don't care how hard I shake the rope, how quickly I shake the rope, how slowly I shake the rope. Whatever I do on my end of the rope doesn't matter, right? Not just tension, but properties of the material, right? So properties of the medium, okay? That includes tension, that includes temperature. For sound waves and stuff and water, it deals with pressure and density, all right? I'm gonna give you a formula we're going to use a little later, right? We're never gonna really use this to solve a problem, but when you look at the formula, it should make sense. That's all I want, right? Like, I want you to look at it and tell me the story, okay? The speed in a string, right? Right, so this is my string. This is V. In a string, the speed of the wave is the square root of the tension all over, I forget what letter they use for this. It's not rho. Hold on. Okay, linear mass density symbol. Oh, they do use mu. Okay, see, I was gonna use mu, but I was like, wait, that's the friction coefficient. It uses the same thing. All right. So it's tension over mu, and this is not a friction coefficient. Okay, this mu is linear mass density. Right. So mu is mass over length. Okay, that's it. So your traditional definition of density that you learned in chemistry is actually incorrect. Density is not mass per unit volume. That's volume mass density. There's all different types of density, right? What do you mean, Mr. So? Like, yeah, why is mass per unit volume like the one authoritative density? It isn't, right? You look at city planning, people look at population density. What's that in? That's people per square meter. And there's also area density, mass area density, right? I can look at really thin paper like this, okay? This is from one of my figure drawing things earlier in the week. And I can look at, I don't know if that's really school appropriate. Whatever, it's art, okay? Did you just call what you do art? Whatever, guys. And where's sticker paper? Obviously, I get this cardboard piece, right? So out of these two materials, like this has a much higher mass per unit area, right? Kilograms per meter squared density, right? So there's population per square meter, there's kilograms per square meter, there's kilograms per meter cubed, right? Which is like the traditional mass over volume density that we've been dealing with, that you have been dealing with since like chemistry and stuff. But there's also mass per unit length, right? And that's going to differentiate like a really thin string to like a really thick like coil spring or something, or like a really thick wire, right? Like clearly, right? This coil of wire, right, has a much higher linear mass density, that's kilograms per meter, than the string that's attached to my needle here, right? This has a much thicker or much greater linear mass density, right? So that's all this is really saying, right? So the speed of a wave, like the higher the tension, right, the speed should increase. I hope that's what we saw, right? That's number 2 from the work from our lab, right? The only thing that really did affect the speed was the tension, right? And if you actually graphed it out, it would be a square root relationship. How do I confirm that? I'll graph v versus square root of ft, or v squared versus ft, and it should give me a straight line, right? Yeah, so the tighter the rope, the higher the speed, and also it's over density. So the more dense the rope is, like the thicker it is, right? Or the more mass it has per unit length, the slower the wave is going to be. You can kind of imagine this by like sending a wave through like a string, right? Like a really thin string, it'll travel, and trying to send a wave through like a really thick, heavy chain, like a really heavy chain. Like you do that, like the wave's gonna be super slow. I have chains on my mind because I'm in the market for a bike, and all my friends are telling me to get a super cheap bike because bikes are stolen all the time. So then I was like in the market for I was like doing some market research for like chains and like bike locks and stuff. And what I learned is there's really nothing you can do to prevent your bike from being stolen. Like yeah, and that makes me really sad. You know, I had a bike in college and it was stolen my sophomore year. Funny story though, I found it. I filed a report with like the campus security officers. I showed them my proof of purchase. So they cut the lock for me that the other guy had now put on. And I rode my bike for the rest of sophomore year and the first half of junior year. And then in the middle of junior year, it got stolen a second time. And it's like, you know what? I'm tired of this. So ever since then, how long ago is that? My junior year. That was almost 22 years ago, right? Like I haven't ridden a bike since, and I really want one now again, just to like get around the city. Especially since I really don't want to ride public transit right now. Even though they're deep cleaning the trains, it's just not the best idea, I think, personally. Yeah, and my apartment doesn't really have room to store a bike. That's the problem, right? So, um, yeah, I really don't know what to do. Yeah, there are some likes that are like bolt cutter proof, but if you walk around with like a portable, like it's not a chainsaw, but it's like the circular saw. Those things cut through anything, and it's just sad that like there are people that do that for a living. You know, it's like, do you understand? Like a bike is part of people's livelihoods and stuff. Like I don't know, man. This makes me really sad. Um, yeah, so that's something I've been thinking about. Anyways, so I should use city. Yona, have you ridden a city bike? They're so heavy. I tried to bike up. I tried to bike across the Brooklyn Bridge with a city bike, and I did it, but my legs killed me the next day. Like, people severely underestimate like how much of an incline the bridges are, but if you've ever stood under a bridge and you look how tall it is, it's almost like 15 or 20 stories high, and you got to bike up that, right? Um, and that was a pain. City bikes are so heavy. Now, is it as heavy as like a normal bike plus carrying like a heavy duty bike lock? Maybe it's comparable. I don't know. Still looking into it. Anyways, let's get back to the information at hand, right? So, obviously, if you get like a heavy chain, like the really heavy duty bike locks are made out of, the wave is also going to be slow there. So there we can answer our question. Why is this simulation better? URL versus IRL? Because the only way to get the rope really straight in real life is with a really high tension. And with a really high tension, the wave speed's just too high. And you can't see it. And you can see this when you pluck a guitar string. Like when you pluck a guitar string, you don't see the wave go side to side, right? It's just way too fast. And we're going to get back to a guitar string in a little bit, okay? So let's move on to the rest of the mini lab, right? So number 3, change the frequency to whatever you want. What is the relationship between frequency and the wavelength? So you should have seen that the frequency increases as the frequency increases, the wavelength decreases, and as the frequency decreases, the wavelength increases, right? So this is what? This is a high frequency. This is a low frequency, right? And I can tell that just by the wavelength. What formula justifies this? Well, V equals lambda times frequency. As frequency goes up, lambda goes down, as long as what? As long as what? Biking upwards doesn't suck if your bike is lightweight. Anyways, but thank you for the suggestion, Leona. That's very sweet. You're so sweet. Frequency and wavelength only have an inverse relationship. Like as one goes up, the other goes down. As long as what? As long as speed is constant. Thank you, sweet Yona. Okay, right? If V is constant, then if frequency goes up, wavelength can go down, right? So it's only when V is constant. Why is V constant? Because I'm not changing the material, right? All I'm doing is changing how much I like shake the rope, right? That's not changing V at all, right? Okay, amazing. Thank you. All right, number 4. Using the same equation, the ruler function determine the speed of the wave at your given tension, which is the highest tension. I don't know, did you guys get around 6? I forget what the number is. Is it around 6 meters per second or centimeters per second? Like 0.06? Or was it 4 centimeters? It's like 6.3, 6.2. Good. Yeah, that's what we should be getting. Amazing. Okay. The cool thing you can do is like after you like find the formula, right? By measuring the frequency and the wavelength and stuff, you could actually just press play and have it run for 1 second and pause it and double check to see if the crest really did travel 6.3 centimeters in 1 second, which it should. Be careful though, because there's a slow-mo function and a regular motion function. So make sure you're not on the slow-mo function if you're trying to test that out to see if it really does travel at 6.3 centimeters in 1 second or 3 centimeters in half a second, you know. That's cool. Amazing. Thank you, Sarah. Becky, Ethan, Chris, you still there? Let's see. Moving on. Number 5. Here's part 2, right? So hit pause, restart. Now we're going to go back to manual mode, but more importantly, we are going to have the string clamped down on the right side. So this is what's known as a fixed end, not an open end. Okay. Hey, Chris. Good to see you. It's okay. Not a big deal, Chris. And I want you to make observations between like waves that you sound and the waves that return, right? And you should make 3 observations, okay? Type them in the chat. I want to see what we all found. What are the 3 observations you can notice about the reflection compared to the original incident wave? All right, so wavelength remains the same. That's good. What else remains the same? Speed is the same. Excellent, Sarah. Anybody else? There's one really important thing about the reflected wave compared to the incident wave. Direction and orientation changed, right? Exactly. So there's a 4th one, I guess. 2. Because originally I was never even thinking about wavelength, but I guess wavelength does remain the same. Frequency period, all that stuff, yeah, that's not what I'm looking for. The amplitude. The amplitude is the same, right? So the main 3 observations that we should have seen were that speed is the same once it's reflected. Why is the speed the same? Because the reflected wave is still traveling in the same medium as the old wave, right? As the incident wave. That's a vocab term, incident, right? It just means like incoming or the original one or the wave that is like put in, the wave that's going in, and not coming out. This is the way I would describe incident. You can interpret it literally as like an incident or an incidence, like it is the wave that happens, right? And the reflection is what comes afterwards. Okay. So speed's the same, amplitude is the same, and most importantly, the orientation is flipped. Like an upward pulse becomes upside down, and a downward pulse becomes right side up. That's huge. It's huge, okay? All right. Okay. Now that we have those under our belts, okay? Get super pumped for this next revelation, okay? Sorry, I just got a weird email. Does this switch of orientation occur with other waves? Yes, at fixed ends. So at the frequency that I gave you, right, which would be 0.75 hertz, the last observation you should have made was you should have created a very basic standing wave. What is a standing wave? A standing wave is a wave that appears to not move side to side, right? It's still, right? All it does is it's just like a jump rope. It just goes up and down, right? So this is a standing wave, right? It doesn't look like there's any side-to-side motion, but what you should know is that this standing wave is the superposition of a wave I'm sending this way and its reflection. And when those two waves interfere with each other, they produce this standing wave, okay? There are a lot of different types of standing waves, right? I can create this one too. Wait, sorry, there's not enough tension. So there's this one. Wait. Yeah, I'm gonna do it from here. It's much easier. Okay, so there's this standing wave. Okay, and then there's this one. Jesus, sorry. Right, so, and there's even more. But yeah, and it looks like it's called a standing wave because it just stands there. Great song, by the way, Flight of the Conchords, if you guys want to look at that. Okay. It's Inner City Living, I think. Oh no, Inner City Pressure. Yeah, Flight of the Conchords. Inner City Pressure. Yeah. There's a line of the song, there's a lyric that says, "You just stand there." Right? Yeah, so the wave appears just to be standing, but it's not. It's actually moving side to side. There's just two waves moving side to side at the same time, right? And the way they interfere with each other creates that really cool interference pattern that's known as a standing wave. Okay? Standing waves have so many important implications for physics, in classical physics and quantum physics, when you're talking about modes and Fourier analysis and stuff like that. So we are going to look at that in a lot of detail, so get pumped. We're gonna do something very similar today as we did yesterday. I'm gonna end the stream now, and gonna give you a short video to watch, and I want you to type up a couple of reflections on what you see, and hopefully it'll make standing waves make a lot more sense. And tomorrow we're gonna really look at standing waves in a lot of detail, all right? So tomorrow will probably be pretty close to a college level lecture on standing waves. So get pumped about that, and I will see you tomorrow, all right? Thanks so much for tuning in. Be sure to hit subscribe and slap that like button, please. And that's it. Bye. Have a great day.